Well, good morning, everyone. We are here to continue our discussion of mechanical testing methods, and currently we are involved with the tensile test. And we'll give more specifics on that here in just a moment. But I wanted to share with you from last video number 4. This happens to be video number 5. And I'll try to make sure this one gets titled like the other one somehow didn't. But at any rate, this is video number 5 and board number 1. And then we're going to talk about this basic standard ASTM tests for determining strength of metals. Not all of the tests, but the major ones here, and especially the tensile test, which we're going to go through in detail. So, first one, of course, as we said, I give you 3 columns here. A stress column, kind of what stress they're undergoing, the specimens. And then what ASTM standard, American Society of Testing of Materials, testing and materials, a little bit of that later, but ASTM standard is called the E8 standard. That's what you'll be using in the lab for doing tensile tests. And then over here, I list the scope and or properties that are gained from that particular test. And this first one is probably the most versatile of all and most widely used, this E8 ASTM standard test, tensile test. And all of these, under the scope and property, all of these are going to be yielding values, of course, numbers, data. And these values are obtained from the stress-strain curve. The data on that stress-strain curve along with the points on that stress-strain curve, all of these values from these properties are obtained from this one stress-strain curve, which we'll go over hopefully on this video as well later on. So, but let's look at this thing again, the E8 standard for the tensile test. Look at all what you can obtain from this test. First and foremost, under the strength category, there's 3 basic, really key points that you can obtain strength-wise from this tensile test vis-a-vis the stress-strain curve. But you can get the overall tensile strength, which is sigma max, all right? Sigma max, and we showed that, and I'll maybe if I can find it again, show that on that chart, the table materials properties, the overall tensile strength, it's sigma max. Also, you get the yield strength, okay, which is sigma y or sigma yield. All right, very important. These 2 points are the most prominent points on that stress-strain diagram. And along with that yield strength value, you also actually find the yield point, okay, the yield point, which is going to be, again, a combination of stress and elongation or strain to find that exactly yield point on that curve. And we'll give an example of that later. Okay, so the other property is ductility property, because you're also, along with getting data for pulling forces on here and tension, you're also getting ductility data in terms of percent elongation, how much this specimen is stretching. And let me get a specimen here. I got one. This is a small tabletop tensile testing machine, but anyway, this shows you what the specimen looks like. So you can see it would be screwed into both these fixtures, top and bottom, and I'll get in detail of that later. But this is being pulled upon, slowly pulled upon. Okay, so you're going to be gaining a dimension, the elongation, and ultimately the percent elongation involved in that, which is again a form of determining, characterizing ductility as a property, and then. The reduction of area, because there's a relationship between elongation and transverse strain as well, axial strain and transverse strain. So this is going to be in a ductile material. This is going to be necking down. That cross-sectional area is going to be reducing as the pull of the tension continues. And the other thing, remarkably, another property called toughness, which we'll get into details of these later on. In the semester, probably the next set of subject matters, areas we'll cover. But at any rate, toughness you can actually just get a comparative value between 2 different materials just by looking at the total area under that stress-strain curve. So very, very valuable test. Very, very valuable diagram, the stress strain diagram. So a lot of information, a lot of data comes from this test. That's why it's so very important. Now I will mention a couple other tests. Now this is for primarily for mostly ductile, some and non-ductile, but I'll show you the difference in the diagrams. But for mostly, let's put it this way, for ferrous-based metals usually, but not always. But there are specifics for aluminum and magnesium alloys, the same similar test, but it's the E557 ASTM standard test because they're a little bit, they behave differently. These do not have, along with titanium, do not have a well-defined yield point. Okay, so there's a slightly different test methodology used in those, but this is an E557 test for that. And then the E9 is the ASTM. Now this is all about compressive properties, which is of course all associated with malleability. Tension is all associated with the property of ductility. Malleability is how much a material can withstand from a compression standpoint, from a compression mode. So they have a standard test E9, which is compressive, and guess what? You can use the same testing piece of equipment. You can either pull something or you can compress something, depending on which way the crossheads are moving, up or down or together. So that's a really good advantage of having that machine being able to do compressive and tensile based properties. So, at any rate, but ultimately, before we leave, maybe not today, but we will discuss what true strength considerations are. These are pure, strength considerations based on just the material. But there's some other things involved when you're looking for ultimately what a true strength of a material and/or a component might be, and we'll address those a little bit later. So let me remove this board and bring up the next board here and make sure it's completely aligned. All right. Let's see what that looks like on the camera. Let's see. Move it up a little bit. Okay, about right there. Okay. Yeah, that's good. So again, this is board 2 for video 5 on 3228 mechanical test methods, and what we're going to be talking about specifically right now is the tensile test itself. And what better way to introduce that is using the actual device here. This is the stress strain testing, or we call it the tensile testing machine. This is just a basic configuration of what this machine looks like. This can be powered either with hydraulics or it can be powered mechanically. I got a picture of that here somewhere. Well, thought I did. Be behind this. No. Oh, it's over there. So anyway, that doesn't matter. But anyway, these crossheads can be moved mechanically by turning these screw threads, or it can be on a hydraulic piston cylinder kind of arrangement. So either way, but you can get, as you can see, you can be pulling something apart or you can be pushing or compressing something. Okay, so essentially we've got, and now this is showing the load cell up here. The load cell is going to be determining the force as you slowly apply force to this in a pulling mode. But a lot of times the load cell are down in the bottom. It just depends upon the machine and the manufacturer. But essentially what you've got here is this test specimen. Again, showing you a good representation of a test specimen here. Locked into these, the top crosshead and the lower crosshead with these fixtures. All right. And by the way, this is not a standard ASTM like this one is. This is a reduced version because this is a much greater. This is very small, probably only like 3/16 diameter, where this is 505 thousandths, so over half an inch in diameter. Where the gauge length is, but it's still a good representation. I'll just leave it there. But at any rate, so this is fixed together in these two devices here, and then slowly starts to pull this thing apart. Now, so you're getting two sets of data here, because attached to this is this fancy schmancy device called extensiometer. An extensiometer. Very important because this is what's going to measure the elongation. Because you can't see here, but these are the gauge length. The gauge length here is usually 2 inches, all right? Whereas the overall reduced neck down section is 2 1/4. And the reason they neck this down is because they want the failure to occur somewhere in here. That's why they neck this thing down, to reduce the area slightly. Because you can see it's 750 thousandths diameter here and 505 thousandths in the neck area. So anyway, you would measure the gauge length, and usually something like this is about 2 inches. And usually there's a mark. And on this little specimen, you probably can't see it, but there's a little dot there and a little dot there and a little indentation. That would be the gauge length right here. And you can measure that with a set of calipers to tell exactly what it is prior to the test, all right? Then you would put this in, again, the machine, and then put the extensiometer to it, which is just an electronic device that's going to be measuring the increased length as this thing begins to pull. And so that's what this extensiometer is doing. So again, the 2 sets of data points you're getting here is a force reading. Every time you increase this thing and start to pull this thing apart, you're increasing the force, all right, which is going to be a data that you would feed into the stress strain diagram. More about that later when we do the diagram. But at any rate, and then the other piece of data you'll be getting, every time you stop and take a data point for force, you'd stop and take a data point on the extensiometer. It would tell you how much incrementally this thing is increasing in length, or again, the elongation. So very, very important. Otherwise, if this wasn't there, you'd have to physically take calipers and measure the gauge length each time you stop and do this. But this is going to do this electronically for you. Now, one key note to make here is that the extensiometer does not stay there the entire time of the test, because when you eventually hit the yield point, and you'll know when you hit the yield point, and I'll tell you why you know the yield point. You'll know the yield point later when we get into the diagram, because I can show it to you and represent it. But when you hit that yield point and you verify that, yes, okay, we just did the yield point, there will be no more elastic deformation taking place. It will only be plastic deformation or permanent deformation, okay? Non-recoverable deformation. At that point, you would go ahead and say, okay, that enough is enough. You would pull this off, because otherwise, I mean, this thing just has a certain limitation, and then when this thing does break, you don't want this in the fray of the fracture, mechanism. So you would take this off after the yield point, or the yield stress, eventually calculated the yield stress, what that is. But eventually what you're trying to do is, again, take this off right after you've determined that you have reached the yield point of that specimen, okay? So extensiometer, 2 sets of data points. Here's the specimen itself here again. And so there's lots of different types of specimens. They're not always round. Sometimes they can be flat, different types based on different types of materials, etc., etc. But any rate, so this is the test itself, and so let's look at this, the tensile test. Okay, I've briefly probably commented on all these, but it's the most commonly used mechanical property test. But again, if you go back to that first board, you saw all the various types of properties, both from strength, from ductility, and from toughness, that can be achieved from this test. So it's very widely and commonly used. Its chief use, of course, is to determine the property associated with the elastic design of structures and components. Okay, the elastic design. In other words, the Hookean type materials are what we're talking about here. The elastic design of structures, components, mechanical elements, whatever that might be. All right. It also, though, as I've said, reveals information on the plasticity and the fracture of a material, because from this stress strain diagram, you see, you're going to see an indication of just how ductile this material is, and there's we can determine or state if a material is ductile based upon its percent elongation value. So you're going to see a lot about its plasticity and a lot about also how it fractures. All right, and you very definitely, if you had no idea what material you're using, putting in there, and I'll show you some examples uh, of that. Of a ductile material and a non-ductile material, but on the diagram you'll definitely see a definitive difference in just looking at the two diagrams, which material was ductile, which material was non-ductile or brittle. Okay. All right. So advantages here is that the stress states are very well established in these tests. You know, they've been doing this for so long. So the stress states are well established in how they react. The test has also been very carefully standardized worldwide. All right, and so it's a very valuable test. You compare something here to something there. Very well standardized. And essentially a relatively easy and inexpensive test. A relatively easy and inexpensive test. Now, you know, these machines can range. Ours, we've had several of them, but obviously they can range in size from very large. We have one large one in there, and then we have a sort of couple of medium-sized ones, and then you can get them on a tabletop mount also. And as a matter of fact, a couple of years ago now, I proposed a Design 1 project for the students to design and build a hand crank tensile test machine, and it wasn't on a vertical mount, it was on a horizontal mount, and they could just hand crank this thing at the same time. They could be reading, the force that it was pulling on that specimen, and then they could measure the extension of that, but it was all on a hand crank model for, you know, just showing the system, showing the proof of concept of what this tensile test is about, especially if, you know, showing, you know, young folks in high school and such. It's kind of what this is all about, since it's such an important test, especially for mechanical folks. So and that currently is sitting in my office, but I will get that out and put it in the lab, because it was finally turned over to me. Somebody else on campus was using it. That was such a great design, of course. But at any rate, we got it back, and now we're going to put it back in our lab. So they come in a wide variety of sizes and scales and such. So that's the machine itself, and unfortunately you won't be able to physically get your hands on it this semester, but maybe next semester there'll be opportunities for you to do that. Now I'm going to step away from the table briefly and see if I can find those other specimens for you. Rattling stuff. Okay, so the timer's about to go off, so I have to end this. But here is a couple of ductile pieces that you can see have broken, and we're going to talk about the actual geometric shape of these when they do break. Now this is aluminum, this is steel, but this is what they look like, and you can see on this one specifically, I think, hopefully, it's kind of necked down. You can see how it's kind of got this curve to it around there. So that's the necking down of it. And essentially what you're seeing, the formation, the geometric formation on a ductile material is what we call a cup and cone formation. And more about that specifics later. But when you see a cup and cone, so this would be the cup and this would be the cone. When you see this on a specimen that's been pulled apart, you obviously would know that that it was a ductile type material. Okay. Now this happens to be this is an engine head stud off a Porsche 911 engine that happened to be mine. But this was supposed to be a ductile material, turned out not to be a ductile material. Maybe more about the specifics of this later, but this is something that turned out, like I said, to be a very brittle material that caused engine problems. At any rate, so that's that. And what I'll do is on the start of the next board, I will go through the diagram, stress strain diagram, with some specifics, and then we'll move on. So just ran out of time a little bit, so we'll stop here and continue on.